Here you are having 10 questions from atomic structure mainly, and there will be some chemical calculation MCQs also. Okay, and I try to cover all the possible question types in our A-level chemistry paper. And you can see here you are having the question number 9 and 10 from first statement, second statement questions. And then you are having ABCD type question, 2 questions also, right? And there are 6 ordinary type MCQs. Here the first one is from Planck equation, a problem. Here it is telling blue light, they gave the wavelength here, blue light 490 nanometer. So this is what we call as lambda wavelength, okay, and produces 3 joules of energy per second. How long does the bulb take to generate 1 into 10 to the power 20 photons? Okay, so from this lambda wavelength, we can find the energy of 1 photon. Okay, so energy of 1 photon. So the formula is equal h nu originally. Nu stands for the frequency, but we can replace nu using wavelength because we know C equal nu lambda. Therefore, if we subjected nu, you can say it is C over lambda. So by substituting that, we can write the new formula equal hc over lambda. Okay, so this is the formula for finding energy of 1 photon equal hc over lambda. So now we know the lambda and we know the speed of light c. So by substituting those values and also the Planck constant, you can find the energy of 1 photon. Okay, so remember what we are finding. Okay, just let's not substitute just values. Okay, let's do that one with knowing the purpose also. Okay, so you can find the energy of 1 photon. So before going into substitutions or any of that, let's stick to the method first. Okay, let's see what's the method this one. Right now, however, we are finding the energy of 1 photon. Okay, so then next thing is they are asking for not just for 1 photon, right? So they are asking this question about this number of photons, 1 into 10 to the power 20 photons. So then we can think about how to relate that value. So now we can find energy of 1 into 10 to the power 20 photons. So it's a very large number. Okay, so if you want to find energy of that number of photons, let's say that number is equal to capital N, right? So what should we do? We have to multiply that energy of 1 photon by that particular number. Okay, so if you know the energy of 1 photon, you can find the energy of 10 to the power 20 photons by just multiplying by it. Okay, so it's very simple maths, right? Isn't it? Then you can now that's their total energy, no? And then they are telling you, Lamai, you notice this statement: 3 joules of energy per second. Okay, 3 joules of energy per second. That means within 1 second they release 3 joules. Or in other words, we can say to release 3 joules, it takes 1 second. Let's say this energy is X. So if you want to release X amount of joules, you have to find what is the time it will take. So that's the final answer. It will be one of these 5 answers. You can choose it. So this is the method. Think about the method one more time. You are finding energy of 1 photon and then multiply it by 10 to the power 20 to find the total energy release. Then you can use this 3 joules per second thing and find the number of seconds or the time spent to release that amount of joules. Is that clear for you? So now let's substitute the values and see if the answer is coming. The answer is coming. Okay, right. So H value 6.626 into 10 to the power minus 34 joule seconds. Then your speed of light 3 into 10 to the power 8 ms minus 1. Remember to substitute SI units here. Okay, otherwise units will not be cancelled. I hope you can understand it. So here, if you substitute 490 nanometers, it's not going to work. You know, nanometers will not cancel into any of these units. So you need to convert 490 nanometers into meters first. Okay, so you know that Lamai 1 nanometer equal to 1 into 10 to the power minus 9 meters, isn't it? So if you are having 490 nanometers, then it will be equal to 490 into 10 to the power minus 9 meters. So this one, if you simplify it a little bit more, you can tell 4.9 into 10 to the power minus 7 meters, isn't it? Right? You can substitute this value for the lambda. So let's do it now. 4.9 into 10 to the power minus 7 meters. So now you can see easily units are cancelling off, isn't it? So you can cancel the meters, you can cancel the seconds, and you will be getting the answer in joules. So it's a very important thing to convert units. Remember that, okay? Now, you can see it's not divisible, obviously. So I'm not going to divide those, right? Instead of that, what I'm trying to do is I'm going to round it off, because you can see there's a much difference between the answers. 3 seconds, 7 seconds, 10 seconds, like that, there's a gap. So no point of exactly dividing. We can round it off. Okay, so those things you learn from MCQs, right? Okay, so that's why we are doing this class also. So to teach you or to practice with you how the methods, what are the methods we should use in these questions. Okay, right. Now if you round it off roughly, I can say 6.6. Okay, and 3, and let's say it as 5. Then 10 to the powers, you can simplify here minus 7, minus 34. You can simplify it like minus 27 will come, isn't it? Minus 27, and this 8 minus 90. Okay, so just keep it in that way. 6.6 into 0.6 into 10 to the power minus 19 joules. That's the energy of one photon, isn't it? Energy of one photon. Then what we need is energy of 10 to the power 20 photons. Now let's see how to find that value. So this value 10 to the power minus 19, our energy of one photon, we are multiplying it by 10 to the power 20, our number of photons. Now we can simplify minus 19 and minus 20. You can see 6.6 into 6. That is the number of joules for 10 to the power 20 photons. Now that is our value of x. Okay, so 6.6 into 6 joules. So now we need to find what is the time required for that particular amount of joules. Okay, so what do? We divide it by 3. Then you will be finding the number of seconds. Divided by 3 and multiply by 1. Okay, so just direct proportionals, isn't it? If you lit that bulb for like 2 seconds, then you get 6 joules, no? Like that. If you want 12 joules, then you need to light it up to 4 seconds. Apply that thing. Okay, so then what do we do? If you want to find the time, 3, we can say joules per second if you want, right? Then you will be getting the answer in seconds. So that's why I didn't simplify here. You can see it's cancelling off. 13.2 seconds. Okay, and you can see that answer is not there. Right? And we should not expect that also. Why? Because we did a rounding off here. Instead of 6.626, I took 6.6. And instead of 4.9, I took something higher than that. Because my number is higher, 4.9 is, 5 is larger than 4.9. Therefore, I should expect a lesser answer than the actual answer. Okay, so then my actual answer should be something little bit greater than 13.2. So the little bit greater than 13.2 is 13.5. Okay, so that's how we come to the answer with minimum simplifications, right? So something extra I need to tell you here. So here the joules per second, that unit I hope it is familiar with you. If you divided energy in physics by time, what do you get? You get the power, isn't it? Power. So that's energy 3 joules per 1 second. That means Lamai, the power is 3 watt, capital W. isn't it? So now they didn't do it here, but I have seen some school MCQs, right? Instead of telling you that 3 joules per second thing, they are giving you the power of the bulb. Okay, so you need to understand it is the same as joules per second. So something extra. Remember that also. So this is our second question. So which of the following is incorrect statement? Alpha radiation emitted from a radioactive material deflects perpendicular in a magnetic field. So here's the point. Okay, if anything has a charge, let's say positive or negative, whatever, right? If any material has a charge, alpha particle, maybe beta particle or proton, electron, whatever, they will deflect in electrical and magnetic fields. Okay, so deflect means they will change their pathway. So let's say they are traveling in a straight line, but if you are putting a magnetic field in either sides, though, so then it will bend. So then they are traveling in a straight line. You are putting a electrical field. Then what will happen? Then they will attracted towards the electrical field. Okay, here the magnetic field thing, they are not attracting toward the magnetic field, any of the poles. Okay, so they will deflect perpendicular to the magnetic field. So you can simply apply your O-level Fleming's left-hand rule and see how the forces and fields are working. So then it will be confirming you that in magnetic field, the whatever the charge particle is bending in perpendicular direction. Okay, right. So then alpha particle, we need to think here whether the alpha particle has a charge or not. Okay, so alpha particle is Lamai. You can see it is positively charged. Actually, the relative charge is +2 because alpha particles are the helium nuclei. Helium nucleus, you have +2 charge, no, isn't it? So therefore, alpha radiation will be bent. Okay, so then that is correct. So any charge particle deflects in electrical and magnetic field. So remember that is the explanation for the question, for the first statement. Then you go for the second one, giving a clear sharp shadow behind the anode. Okay, when a metal cross is placed in the pathway of the cathode rays, you have seen this thing, but it is not confirming the wave character. That is wrong. So clear sharp shadow confirms what? It is confirming that cathode rays travel in straight lines. That's what it is telling, not the wave character. Okay, so if you want to observe the wave character, I will tell you, you can search the internet and see. This experiment is not in our syllabus. If you want to check the wave character, you have to do the double slit experiment. Double slit experiment, not the not this one. Okay, this is for cathode ray experiments, and it is telling you that cathode rays are traveling in straight lines. Okay, so then it is wrong. So that's your answer. They are asking for the incorrect one. Now here you have the incorrect one. So second one is the answer. So then that means other three answers, 3, 4, 5 are correct. So let's briefly look into them and see how they have become correct. Okay, so third one, in gold foil experiment, the deflection of fewer alpha particles in small angles. You have to see whether first that is correct or not. So in gold foil experiment, you should remember that there's a thin gold foil in the pathway of anode rays or alpha particles. Then what will happen? Those alpha particles, most of them will go through without any problem because the space of the atom is mostly empty, and only some particles, only very few particles will bend, change their pathway because of the positive repulsion that is exerted from the nucleus. Okay, and very few particles will bounce back because they hit directly on the nucleus. Okay, so therefore this is third statement is correct. So it is telling you that fewer alpha particles are bending in small angles due to existence of small positive charge particle. That is very correct, and you can say repulsion from this. very small positive charge particle. Now we know it as the nucleus. You can say nucleus repel the alpha particle, because alpha particle is also having a positive charge. Nucleus is also having a positive charge. So it's a fundamental thing that we know. Positive repels, or the similar charges repels. Okay. And fourth one, canal rays. Canal rays are the positive particles formed within the anode ray tube by losing of electrons. Okay, so when cathode rays are traveling very fast within the cathode ray tube, cathode rays are hitting on the gas particles, gases. So then gases will be ionized into their respective ion. So that what we observe as the anode rays. Okay, so if you want to observe anode rays, you should have holes in the cathode. Okay, that's a different story. But however, let's see about this statement. Although the canal rays are not exactly formed at the positive electrode or anode, yeah, that's true. It's formed in the medium. Since they are formed away from the cathode and close to anode, they are known as anode rays. That's very true. That's how we name anode rays. So at the my cathode rays, they are starting from cathode. The electrons are jumping from cathode to anode. That's 100% correct. But here, even though we call them as anode rays here, they are not exactly starting from anode. They are starting near the space of the anode. Because how anode rays are formed, you have to study. Anode rays are formed by losing electrons from atoms. Okay, gas atoms. So that is happening within the medium, not from the electrode. Okay, but we call them as anode rays because they are coming from the direction of the anode, not exactly starting from the anode, but near from that. And the last statement about successive ionization energy. Here what is happening, you are removing electrons one by one. So you can follow the values 178, 312. There's not much higher value, but you can see when you remove the third electrons, IE3, third ionization energy is very high. The reason is third one is removed, very high. Therefore, third electron is removed from stable configuration. Stable configuration. That means there are two electrons in outer shell. These two electrons are in the outer shell. So if you remove those two electrons, then it has become a noble gas configuration, isn't it? So if you are having two electrons in the outer shell, that means it should be belong to the second group. Understood? So that is very correct. You can draw an explanation using one of the second group elements. Let's take beryllium. Beryllium configuration is 1:2:2. If you draw the ionization energies, 2:2, two electrons are easily removed, but removing 1:2 electrons are difficult. Sorry, because of the stability of the helium configuration. So you can now confirm these two electrons are in the outer shell. So these are the axes, energy and the electron. So this is IE1, IE2, IE3, which is higher, 1700 something, and IE4. Okay, so that's our explanation for the second MCQ. Third, fourth, fifth are chemical calculations, and of course, sixth one also. There are 4 chemical calculations. Just to remind what we learned earlier. Now let's go to the third MCQ. So here the question is telling 74.2 grams of pure sodium carbonate is dissolved in 150 cubic centimeters of 5 mole per decimeter cube concentrated calcium nitrate solution. So now you can see pure sodium carbonate mass is there. From that you can find the moles of sodium carbonate. Here in the question they haven't given the relative atomic masses, but let's say we are having them. So we can find moles of sodium carbonate. And also we can find moles of calcium nitrate too. Okay, so those are the two reactants actually in the following balanced chemical reaction you can see. So when you know or when you are given at least two values for the reactant moles, then you have to think whether which one reacts completely. You have to find it. So for this one, we are using a method called ARR, added reacted remaining. By that method, we can find out which one is completely reacting, because that particular reactant is the one that decides the limit of the reaction. So therefore, we call it as the limiting reactor. Okay, according to that number of moles, you can get the products. Okay, so first of all, let's find the molar mass of sodium carbonate. Okay, sodium 23 and carbon 12, oxygen 16 into 3, that means 48. 48 and 12 60, 60 plus here 23 into 2 should be there because there are two sodium atoms now, and that means 60 plus 46, you are having 106 grams per mole. So then to find moles, you can use mass over molar mass formula. 74.2 gram, 106 grams per mole. Then you can see you no need to use any calculator or something, just guess. Okay, guess and think whether your guess is correct. So that's how we have to actually do. So let's say it is 7. So 7 times 100 is 700. 6 times 7 is 42. So you can see it is divisible. So if you multiply 106 into 7, 742 should come. So here you have the 1/10 of that value now. So 0.7 moles you are having from sodium carbonate. Okay, in that way you can simplify. Again, you can find the moles of calcium nitrate by using N equals CV formula. This is the concentration and this is the volume in decimeter cube. You have to do it in decimeter cube, just like in earlier first question. You need to adjust the unit in order to cancel them. So again you are getting 0.75 moles. Okay, now let's apply the ARR method I told. Okay, so added, reacted, remaining. So I'm just considering the same reaction they gave. I'm not going to write it anywhere else. So here we have added from calcium nitrate 0.75, but from sodium carbonate we have added only 0.7. So now since they react in 1:1 ratio, okay, only 0.7 will be spending. Okay, 0.7. So that means the limiting reactant or the one that finishes first is sodium carbonate. The one that finishes first is sodium carbonate. So 0.05 will be remaining from calcium nitrate. That will be the excess reactant. And this will be the limiting reactant for this particular instance. It's not something fixed. You can make sodium carbonate also excess if you add a little bit more. Okay, right. So here you will be having calcium carbonate 0.70 and here 0.7 into 2, that means 1.4. It's not relevant for our question. However, they are asking what is the mass of the dry mass. Here the precipitate is calcium carbonate. You can see the solid symbol. So then now we know the moles. Okay, so let's find out the mass. Calcium carbonate molar mass, again you can find calcium is 40, carbon is 12, and oxygen is 48. If you add them, then you will be having 100 grams per mole. So to find mass, what we are doing is moles into molar mass. 0.7 moles into 100 grams per mole. So then you are having what? 70 grams. So that's our correct answer. Answer number 2. Okay. Let's see our fourth question. Following reaction occur when excess hydrogen. reacts with 1.5 gram mixture of Fe3O4, right? And Fe2O3. So you are having sort of a mixture, I believe. Okay. Then the mass of mixture obtained after the reaction is 1.46 gram. That means some mass is reduced because of the removal of this oxygen, right? So then what they're asking is what is the mass percentage in the mixture? Fe2O3. So there are several methods to do this question. Actually, if you somewhat aware about this lesson, you will figure out the all ways, okay, all other ways. But I'm trying to do just the simplest method as I see now. I'll write few reactions and explain that method to you. Okay, we'll see. So 3Fe2O3 NH2 reacts to form Fe3O4 and water here too. And this is a solid, gas, a solid, and a gas. So it's important to understand the question here. That's why we need physical states. And they are telling it's not only Fe2O3 mixture, it is having Fe3O4 also, some mass. So their total mass was 1.5 grams. Okay, but this Fe3O4 don't undergo any change now, so it's still stay as it is, right? But now the solid mass is 1.46. Now you can see some mass difference. Okay, mass difference is the reason for the mass difference is the removed oxygen. It's not water. Don't say water because hydrogen was already there in the reactant side too. So then you can see clearly the reason for the mass difference is the loss of oxygen atoms as water. Okay, so then if you get the subtraction, to get the difference 1.50 minus 1.46, we will see the mass lost due to oxygen. Okay, so this is the mass of oxygen. What we need is the moles of oxygen to get some idea. Oxygen atoms, okay, don't forget that one. So oxygen atomic mass is 16. So if you divide it, you will see it's divisible for 0.00025. This number of small amount of moles has been produced from oxygen. Okay, so that means, Lamai, here if you consume one oxygen, releases one oxygen, then the reacted Fe2O3 will be 3 times like that. You can see the ratio 1:3:1. Therefore, you can find moles of Fe2O3 is 3 times as the reacted moles of formed moles of oxygen. Okay, that means the removed moles of oxygen. So 0.0, yeah, I'll keep the 16 thing into 3. Okay, then that's the number of moles. They're asking the mass percentage. It's a very simple thing. Fe2O3 percentage composition, what they're asking. You have to divide mass of Fe2O3 by the total mass and multiply by 100%. So mass of Fe2O3 can see 0.04 into 3 over 16. Fe2O3 molar mass, iron 56 no. So 112, 3 oxygen means 48. So it's 160. 160. That's the mass. And divide by the total mass, that's 1.5. and multiply by 100. So let's do the simplification. You can see it's easily divisible. 10, 0.4, we can cut the 3 also, 0.5, then 0.4 over 0.5, division 5. So then 400 division 5, you'll be getting the answer 80, 80%. Okay, so that's our answer for the question. So as I told at the beginning, this is just one method. Yeah? You can use simultaneous equations and that method too. Okay, so you can get that method. I'll briefly tell you. I'm not going to do it here. Just try that at home. Okay, and show me your reviews. Here you can take this mass as x, moles as x. Here this one as y. Okay, and from the same way you can find the moles of this one in terms of x and in terms of y, and then multiply by their molar masses and make them make their sum equal to the given value. Then simplify that simultaneous equation, then you will be finding the moles and then you can get the mass percentages. Very simple. This is our fifth question. 15 cubic centimeters of vinegar solution was added to 15 cubic centimeters of excess barium hydroxide solution. That excess term means something very important. That is, our added vinegar will completely react, and some amount of barium hydroxide will remain also. That is the meaning. Okay. The solution was then diluted to 100 cubic centimeters and 25 was separated. Okay, and then the remaining barium hydroxide, now we know that after the reaction some barium hydroxide will be remaining, no? That amount is found using HCl. That's what they are titrating it for. Okay, so let's put a small diagram in order to understand this one. First, you are having 15 cubic centimeters of acetic acid or vinegar, and then you are adding another 15 cubic centimeters. Now the volume doesn't matter, Lamai. Actually the concentration is a little bit high. They are telling it, however. So then we know that since this is excess, all acetic acid will be reacting and some amount of barium hydroxide is remaining. BOH twice is remaining. Okay, so then you are adding water and you dilute it up to 100 cubic centimeters. From that 100 cubic centimeters, you are taking 25. Okay, you are taking 25. Then you titrate it with HCl. So HCl concentration is 0.1 and the required volume is 10 cubic centimeters. You have to think about how to do the question and start doing. Okay, now let's try. First of all, we can take the reaction between HCl and barium hydroxide. So it's acid-base simple titration. Here 2 HCl is reacting and it takes barium chloride then 2 water. So then 2:1 ratio. We can get the HCl moles actually reacted. 0.1 mole per decimeter cube into 10 centimeter cube. So I converted it into decimeter. Okay. So then I can get 1 into 10 to the power minus 3 moles of HCl is reacted, consumed. So then I can get moles of barium hydroxide is remaining. It is remaining, and don't forget in 25 cm cube. Okay. It's actually half of this value. That means 0.5 into 10 to the power minus 3. But that was actually there in 100 cubic centimeters now. in 100 cubic centimeters. That value will be 4 times like this. That means 2 into 10 to the power minus 3 moles. Okay, so that amount of moles was there remaining. Okay, now let's find moles of barium hydroxide we first added. We have added barium hydroxide, 1 mole per decimeter cube concentration, and 15 into 10 to the power minus 3 dm3. So that means 15 into 10 to the power minus 3 moles we have added. Now you can see only 2 is remaining from that. Therefore we can say reacted barium hydroxide with acetic acid is equal, we have to do the subtraction and see, okay, 13 into 10 to the power minus 3 moles. Now we go for the reaction. Barium hydroxide and acetic acid, that also reacting in 1 is to 2 ratio and 2 watt. So from this reaction you will be getting barium acetate and 2 watt. So what is important is the ratio. Okay, so if you know that the moles of barium hydroxide reacted is 13 into 10 to the power minus 3, 2 times like that. That means 26 into 10 to the power minus 3 moles will be reacting from acetic acid. Okay, now you can find the concentration of acetic acid by simply dividing these moles by volume. Volume is 15 into 10 to the power minus 3 dm3. So you can divide it by 5 and just simply say it should be something little bit closer to 2 but less than 2. You can stick to the value 1.73 is good. Third one. Okay, so that's how you do the fifth question. Now let's do the last chemical calculation. That's also acid-base titration. First, we will draw a diagram for that one. No? So now the barium hydroxide is reacting with both acids. Okay, now let's see. Here, first of all, we will be drawing the diagram like this. Okay, and you can see now there's HCl and H2SO for 2 acids, and we are making a mixture by combining them, joining them. Okay, and that whole mixture we are reacting with barium hydroxide. Now barium hydroxide is also a strong base, and it is reacting completely with both acids. Okay, so that means we need there 2 reactions. So if you take barium hydroxide, the reaction with HCl, it will be like this: barium chloride and water, 2 water. And for the reaction with sulfuric acid, we will be having barium sulfate, BSO4 and 2 water. Here the ratio is 1 is to 2, and here the ratio is 1 is to 1. So it's reacting with both the acids. Now to react with both acids, you can see how much barium hydroxide is consumed. 0.5 into 13 into 10 to the power minus 3. That means 6.5 into 10 to the power minus 3 moles is consumed to react with both acids. Okay. Now we know about HCl. We can find moles of HCl from here. 0.25 into 20. That means number of moles, 2.5 into 2, 5 into 10 to the power minus 3. Okay. Now come to this point, it's very important. If your number of moles of HCl is 5 into 10 to the power minus 3, okay, your barium hydroxide mole should be half from that value. Half from that value. Okay, so that means 2.5 into 10 to the power minus 3. So now from the total value, if 2.5 is consumed for HCl, the remaining should react with H2SO4. Okay, so the reacted amount with H2SO4 will be, yeah, you can subtract and you can get the answer 4 into 10 to the power minus 3. So then H2SO4 moles is also 4 into 10 to the power minus 3. Okay, so what we need is the concentration. 4 into 10 to the power minus 3 moles, I have to divide by the volume of HCl, sorry, H2SO4 we took, it is 10 cubic centimeters. So you will be getting the answer 0.4 mole per decimeter cube. Okay, so answer 1. 2 ABCD questions. Okay, which of the following statements with regard to hydrogen spectrum is correct? So it's asking energy gap between third and fourth lines of the Lyman series equal to the energy gap between first and second lines of the Paschen series. So we have to see whether it is correct. My advice is, Lamai, just draw a few lines to indicate the emission spectrum energy levels. Here now you are having some energy levels, right? Now let's label them. So here is the first energy level and second energy level, third energy level, fourth and fifth. Okay, right. Now let's mark the electron transitions. Okay, electron transitions. So Lyman series is the transitions that are happening to the first energy level. Okay, so this explanation alone is enough for you to learn the whole thing. So therefore, listen very carefully. Now these are the Lyman series lines. So I have drawn 4 lines that are falling to the first energy level. Then if the line is falling to the second energy level, it is belongs to the what? Balmer series, our second set of lines. Then if it is falling to the first energy, third energy level, we call it as the Paschen series. Okay, Paschen series. So these are the lines of the Paschen series. Okay, so now we can write Paschen, then Balmer, then Lyman. Okay, and then if you can, then of course you can label them also. Here L1, L2, L3, L4, like that you can continue. L5, L6 will be there, but I have drawn only 5 energy levels now. Therefore, it will be stopping right here. Then for BAM also we can label B1, B2, B3 like that. So these are BAM series is in the visible region actually. So B1 is red color, B2 is green color, B3 is blue color, and there's one more, B4 will be in violet color. Okay, I haven't drawn B4 here, okay, Lama, don't be confused. And Paschen series, this is P1 and this is P2. Okay, so now let's go to the first statement. Energy difference between third and fourth lines. So here it is, third and fourth lines, this one, is equal to the Paschen series first and second energy gap. That is true. Okay, and it is also equal to the B2 B3 gap also. It is not in the question mentioned, but you can see it from the graph. Okay, B2 B3. Then energy gap between first and second lines of energy levels is smaller than the energy gap between second and third energy levels. That is wrong. What will happen when you move away from the nucleus, the gap between energy levels decreases. Okay, so first and second energy levels gap is larger than the second and third energy level gap. Okay, so therefore B statement is false. H beta line, so actually Balmer series lines are labeled in that way also. This is called H alpha, second line is called H beta, and H gamma, H delta fourth line, like that. So H beta means the second line, which is the green color line. Okay, so the relevant transition is from fourth to second energy level, 4 to second, not 3 to second. So therefore that also wrong. Okay, so everything is there in the diagram. That's what I meant earlier. Okay, you remember this diagram. If you remember this diagram, then that's the end of the story. You can answer any question, right? And D, energy difference between infinite and first energy level. So infinite energy level, and that is actually the ionization energy. It's true, because when you do ionization, what is happening? You are removing that single electron that hydrogen is having. Okay, so that means you are pushing that electron until it reaches the infinite energy level. Okay, so that means the energy gap between infinite and first is represented by the highest frequency line ever possible in the emission spectrum, which is belong to the Lyman series. Okay, so Lyman's highest energy line. Okay, now let's discuss the question number 8. Which of the following statements are true? Canal rays are formed from the gas inside the Crookes tube. Canal rays. Canal rays are the positive rays that we discussed. So that is actually true, because we discussed earlier when high energy electrons are moving in the cathode ray tube, they eventually collide with the molecules. Then they break the molecules into atoms. Then further collisions will cause to ionize electrons from the atom. Okay, so as a result, we will be having H plus ions. So actually that is formed within the cathode ray tube. Okay, cathode ray tube, another name is Crookes tube. Okay, cathode ray tube, then Crookes tube, or you can say discharge tube also. The alpha rays directly coming to the nucleus strike with the nucleus and return back in the coming direction. That is true. That's why in gold foil experiment, very few alpha particles bounce back because of this problem. Okay, that was some unexpected observation. In gold foil experiment, they actually thought that since the gold foil is very thin, Rutherford and his colleagues expected that the alpha particles will pass through the gold foil without any problem, all of them. Okay, but they didn't expect coming back of some particles, alpha particles. So that was something very interesting observation of that experiment, actually unexpected one. So the reason is actually there was a positive dense solid particle within the atom. Okay, that was later named as the nucleus. Atomic absorption spectrum of hydrogen is identical to that of helium. That is wrong. You can't say identical. You can say similar, but not identical. Okay, that term is a very dangerous thing. Similar, but not identical. Okay, because those both are single electron systems. Helium plus also have one electron. Okay, but it is not giving you exactly same emission or absorption spectrum, because of the difference of their energy required to transit. Hydrogen is having a +1 nucleus, but helium is having +2 nucleus. So the nuclear attraction is higher in helium. So the energy required to jump between energy levels is also different. So you can't expect to have the same lines, same energies. Okay, it will be different. And the last one, neutron, is a subatomic particle which stabilizes the nucleus of an atom. Sort of it is correct. That's why actually the nucleus is a neutron is there. Sorry, it is neutral. And Rutherford thought about that. So he found that very small positive particle is there. So he thought how those positive charges not repelling from each other. Then he thought that there must be someone to cancel that repulsion or to keep those positive charges together. Okay, so then he thought about the term neutron. He actually present that term, but he couldn't discover it. Neutron was later discovered by Chadwick. Okay, so then answer is a different combination. So you can say answer 5. Okay, let's see about the ninth question. All the frequencies of emitted radiation of hydrogen emission spectrum in Balmer series is in the visible region. So that one is false. Okay, that is false. Why? Because we know that usually we say Balmer series in the visible region. That's true. But not all lines, isn't it? Only only four transitions are in the visible region. That means if I name the transitions, you can find 3 to 2, then 4 to 2, and then 5 to 2, and 6 to 2. Those are the lines in the visible region. This is red, this is green, this is blue, and this is violet. So what about the other transitions? They are not in the visible region, right? They are in the ultraviolet region. So other transitions means 7 to 2, 8 to 2, like that. Others are in the ultraviolet region because they are having more energy than visible. Is that clear, Lama? This is a very important statement. Huh? So then that statement is wrong because all the frequencies, not all, but the first four lines. Okay. And all the electrons are coming from high energy level to second energy level in the Balmer series. That is correct. So answer 4. Okay. Rutherford's gold foil experiment revealed that there are protons and neutrons. Okay, I just told that one, no, in earlier MCQ. So gold foil experiment didn't reveal anything, any of these two. Okay, don't, even protons was discovered later by Rutherford. So actually what gold foil experiment revealed is existence of nucleus. So this proton by Rutherford later, same scientist but different in times. Okay, I think after 3 or 2 years later. And neutron by Chadwick after I think 20 or 30 years later. 20 years later. Yeah, by Chadwick. So even though we learn it like yesterday and today, right? Those discoveries took like many years. Okay, because within that time, science was developing, just like that. Okay, so then after the development of the science and technology, some groundbreaking discoveries will happen. Okay, right? We'll see. We'll see. Try to be someone like that. Okay. Neutron was discovered by Chadwick, so that's true. But the first statement is false. Again, answer 4. Okay. So that's it for the 10 MCQs.